Okay, guys, in this episode, we're going to talk about core allocation. All right, so what do we mean by core allocation? So an allocation is called core allocation if the following three properties hold. One, it is feasible. Well, normally Pareto optimality already includes the feasibility. I mean, if you're talking about a Pareto optimal allocation, it should be feasible anyway. But I just wanted to sort of underline it. I wanted to underline it anyway. So a core allocation must be feasible. So that's the first property. Second, it must be Pareto efficient. And then finally, third, it should give both agents higher utility than their initial endowments. All right. So I'm going to sort of formally write it down. But let me just say, a few things before going to more formal treatment. Well, up until this point, I mean, when we define Pareto efficiency, we did not really use initial endowments. We used initial endowments just to create the edge workbox and determine the set of feasible allocations. All right. So therefore, Pareto optimality, in order to be able to find Pareto optimal allocations, you have to know the initial endowments the agents bring to the market, because otherwise you cannot know the feasible allocations. However, Pareto optimality or Pareto efficiency does not require the definition of Pareto optimality has nothing to do with the initial endowments. Again, it indirectly is affected by initial endowments because we care about feasibility, but otherwise it's not directly related. However, core allocation is directly related to the initial endowments. All right. So remember, our idea was the following: two agents or more agents get together in a market environment. They bring some good one and good two. All right. There's no production, and so if they want, they can trade these goods. Why do they trade? Well, to make themselves happier. Well, that was the idea. So if they trade, where are they going to end up? Well, they may end up in with their initial endowments, meaning they actually don't trade any goods. If this is what they prefer, well, fine. But they may actually end up somewhere else by trading good one with good two. Well, for those, what should be the solution of a potential trade? We said, well, it should be feasible, the final outcome. It should be Pareto efficient, meaning the agents should improve their situations up to the point where there's no further improvements. All right, so they shouldn't end up some allocation where actually improvement is possible. All right, so if they're going to end up and say, well, I'm happy with this trade, they say, well, that is, in some sense, the best we can achieve, at least jointly. And then finally, obviously, the trade is not compulsory. It's optional. If you don't want to trade, you can always take your initial endowments, go home and enjoy consuming them. So therefore, if you're going to trade and end up with this initial bundle, you should prefer this bundle, all right, to your initial endowments. So that's why we use the idea of core. Well, so more formally, in an environment where there are two agents with those preferences, with these initial endowments, what do we mean by the allocation is a core allocation? As I said, has to be feasible, has to be Pareto efficient. And then third, the agent's utility, agent A and B's utility, when they consume this allocation, should be greater than or equal to, doesn't have to be strictly, right, greater than or equal to their utilities when they consume their initial endowments. All right, so as simple as this. Let me give you one sort of simple example. So consider two agents, A and B, again, two goods, X1 and X2. The utility functions are as follows. The first guy's utility function is Cobb-Douglas type, and so it has a convex indifference curves. And agent B's utility function, however, so these two goods are perfect substitute for him. So nevertheless, we can use margin rate of substitution A equals margin rate of substitution B to find Pareto optimal allocations because, you'll see. And let's suppose the initial endowments are as follows, all right? So the total unit for good 1 and good 2 are 3 units. Well, Let's first find the proto-optimal allocations. All right, so the question is, again, is like, are these guys going to make any trade, or are they going to consume what they are already holding? If they are going to trade, what is the best possible solution? Well, so let's suppose not suppose, but let's try to find the proto-optimal allocations first. Well, the proto-optimality means margin rate of substitution of agent A, which is this term, equals to margin rate of substitution of agent B, which is simply -1. So they must be equal for proto-efficiency. So basically that means whenever agent A's consumption of good 1 equals to agent A's consumption of good 2, well, that point is proto-optimal. All right, so if you drove the Edgeworth box, it's a 3 by 3 box, right? Square. So agent A is on this corner, B is on this corner. So all those points where x1 is equal to xa is basically this 45-degree line. So this 45-degree line, starting from this point up until this point, is the contract curve. So this is the set of all proto-optimal allocations. Contract curve. All right, so remember our final outcome should be feasible, meaning it has to be in this box. It has to be proto-efficient, so I reduced my attention to only those points that are on the contract curve. But which one of them exactly? Well, so basically initial allocation is not proto-efficient, all right? Meaning they should actually do trade, because if they don't do trade, they are going to regret it, because improvement for both agents is possible. So they should trade. All right, but trade and end up what? Well, for this, we use the third concept, core allocation. Well, how do we find it? Well, I mean, simple. You can do it graphically, or you can do it algebraically. So I'm going to do both, but let me just do it mathematically or algebraically. So how do I do that? Well, it's going to be some consumption bundle, right? X1A and X2A, where the utility of agent A has to be greater than or equal to utility of this agent if he consumes his initial endowment, which is 2 and 1. Remember, his utility function is x1 times x2, so therefore initially his utility was 2. So therefore I'm looking for x1a times x2a greater than or equal to 2. Don't forget, proto-optimal allocations must satisfy this, right? So what does that mean? That means, you know, whenever you see x2a, you can just write x1a. So x1a times x1a, which is, by the way, x1a squared, has to be greater than or equal to 2. So therefore, x1a should be greater than or equal to square root of 2. All right? Well, what else? Well, here's the second thing. The agent B should also prefer this bundle, right? So what does that mean? Agent B's utility of x1b and x2b should be greater than or equal to her initial utility, which is 1 plus 2, right? So 3. All right. Well, what is this? Well, that means x1b, because her utility function is x1 plus x2. So x1b plus x2b is greater than or equal to 3. All right. What else do I know? Well, the other thing that I know is the following. So, I mean, here I would like to convert everything as x1a and x2a, all right? Because I have more constraint or condition when we talk about agent A's consumption bundles. So how can I do that? Well, remember x1a and x1b, same for good 2, they are related because of feasibility. So feasibility implies, if you remember, agent A's consumption on good 1 and agent B's consumption on good 1 has to be equal to the total initial endowment of good 1, which is 3. All right, so therefore x1b is nothing but 3 minus x1a. All right, what else? The same thing, it must be true for good 2, right? x2a plus x2b has to be equal to total initial endowment, which is 3. So therefore x2b is nothing but 3 minus x2a. All right, so that means what then? Remember, core allocation means, this sum is greater than or equal to 3, but I can write that sum by basically plugging those things. So that means, let me write it here. So x1b, instead of it, I'm going to write 3 minus x1a, plus, instead of x2b, I'm going to write 3 minus x2a, has to be greater than or equal to 3. So let's do the following. x1a and x2a, let's send them to the other side. But you know what? Before doing it, don't forget, all these core allocations must be proto-efficient, and so therefore whenever I see x2a, I can actually write x1a. All right, so therefore x1a, so it's 2x1a. It's going to be positive when I send them to the other side, and I have 2 3 here, 1 3 here, so it's going to be 3. So what does that mean? That means x1a is less than or equal to 3 over 2. All right. So therefore that means x1a has to be greater than or equal to square root of 2, which I believe is around 1.4 or something, and x1a has to be less than or equal to 3 over 2. So let me bring them together. So x1a has to be less than or equal to 3 over 2, and it has to be greater than or equal to square root of 2. All right? Okay, very good. What else do I know? So, is that it? I mean, I couldn't pin down a specific number for x1a. Is that okay? Well, yes, it is okay. Actually, as you will see next, when I sort of find the core allocations geometrically, you're going to see that that's possible, meaning we may not have just one core allocation. We actually may have, infinitely many core allocations. So how do we know that? Well, so remember, this is the initial endowment. If necessary, I'm going to come back here. So I'm not quite done there. So this is the initial endowment. So what I want is, for the core allocation, I want proto-optimal allocations that are going to give both agent A and B higher utility. So what does that mean? That means I need to find all the points on this contract curve which are going to give higher utility to both agents than this initial endowment. So how can I figure out those points? Well, simple. Draw the indifference curve of agent A and B that are passing through this initial endowment, because those indifference curves are going to give us what the initial utility of agent A and B are, meaning if they consume their initial endowments, those indifference curves indicate the level of utility they are going to get. All right? Well, we know that agent A's utility is a Cobb-Douglas type, so its indifference curve is going to look something like this. Well, what about agent B's utility function? Well, it's going to be x1 plus x2, so it's a straight line. So let me use a blue color for this. And its indifference curve is going to look something like this. Okay, so this is u of B, the blue one, and the black one is the u of A. Well, one question maybe is why they're not tangent to each other at, those points. Well, they can't be, because I am drawing indifference curves of agent A and B that are passing through the initial endowment. All right? And so I know that initial endowment is not proto-efficient. And so all I know is that when I draw these agents' indifference curve passing at and on, the initial endowment, they're not going to be tangent to each other. All right? However, if I draw the indifference curve of agent A on some point here and indifference curve of agent B, well, they are going to be tangent to each other on this contract curve, but outside of it, they're not going to be tangent to each other, right? That's the idea of MRS A equals MRS B gives us the proto-optimal allocations. So anyway, what does that mean? That means remember, the at least as good as set for agent B is, let me use blue color. So all the allocations in this region. What is the at least as good as set for agent B? All the allocations in this region. Well, remember, for core allocations, I am looking feasible allocations, fine. 2, efficient allocations. So I don't really care about those regions. I care about this 45-degree line. And the third thing is that both agents should be getting higher utility. That means optimal allocations that are in the intersection of the at least as good as set of these two agents are the core allocations. All right, so what does that mean? That means this small portion of this contract curve indicates the set of all core allocations in this problem. All right, and in fact they are given by this, right? So what does that mean? That means in this region corresponds to x1, which is greater than square root of 2, less than or equal to 3/2. All right. Yes. What else? Well, we also know that, by the way, square root of 2 is less than 3/2. That we know, but obviously we should also figure out what x2 is, right? Well, remember x1 is equal to x2 because those are the optimal allocations. So therefore, you can just say x1a. Well, let me say it this way: x1a, x2a, comma, x2a. x1b, x2b is a core allocation. So this is the conclusion. If and only if x1a equals x2a, which is less than or equal to 3/2, greater than or equal to square root of 2. So all those points, all right, which are represented on this picture with those points on this red small portion of this 45-degree line, these are all the core allocations. Well, the question is, if these guys trade, which one exactly are they going to end up? Well, we couldn't pin down a unique one single allocation. What we said, look, if these guys really come to this market with these initial endowments, actually, they shouldn't go home without making any trade because they are going to be wasting an opportunity, an improvement. If they trade, they both can end up at higher levels of utilities. So they should trade. That's the first lesson we learn. Well, the second lesson we learn is that, well, if they do trade, right, they should be sort of end up somewhere in this box. And in fact, they should end up somewhere on this contract curve because something outside of this contract curve means there's still an improvement, all right? Meaning both agents can get even happier. So we don't want that to be a final outcome. We want final outcome for that reason to be Pareto efficient. So the third thing we realized is that, or the third lesson we learned is that they shouldn't end up some point here or some point here because those points are worse for agent A than his initial endowment, meaning if they end up somewhere here, agent A is actually going to regret. And if they end up on this part of the contract curve, and this time agent B is actually going to regret. And he's going to veto this trade. He's going to say, hey, you know what? I mean, I'm not going to make this. I'm not going to accept this deal because I can go home and consume my endowment, in which case I'm going to get higher utility anyway. You see what I mean? So they're not actually trade. If they trade, they are supposed to end up somewhere in this red region. Where exactly? We don't say this. We need to impose more structure. But all we can say, they should end up somewhere here. I think that's, pretty narrow, pretty narrow, a good prediction relatively, given that we initially started from this entire, box full of allocations. We ended up on a just very small portion of a straight line. So if they end up, they should end up somewhere there. Next, we are going to talk about what if. So this is, remember, a barter exchange. There's no price. The question is, what if we introduce money and hence price? Would this give us sort of a sharper prediction? So it's coming up next.